Hello, hello. I am Ori Pomerantz, also known as Ori from Lattice, and I am going to talk to you about MAD and the autonomous worlds. Now, how MAD is essentially a way to store data on chain. It's an on chain database with the data stored in key to value tables. And it makes it easy to have an off-chain replica in the client using events. Every time you change the data, it causes an event. Clients can use that to have up-to-date information. This is important because this way, if the user goes into a new area, for example, you don't need to wait for the blockchain for answers from the blockchain to render. You already have all of the information that the blockchain has. You can also use ephemeral tables. These are tables that have no on-chain storage and therefore they are much cheaper, but they use the same data so you can reconstruct the same events, so you can reconstruct the data from those events, and off-chain it's available. Also, there are storage hooks. Storage hooks are code that runs whenever something changes in the data. They can be used for validation. They can be used to create indexes on the data, which are essentially derived tables that start off as that are calculated off of that data, etc. In many ways, MAD is SQLite for EVM. Just like SQLite lets you have SQL in your program, MAD lets you have a database on chain that you can use the way you would use a normal database in your application. What does MAD do? This is what MAD does for data. What does it do for the logic? Well, the logic is stored in systems. The point of systems is that we want to separate the logic from the state. The systems are Solidity contracts. They are very similar to stored procedures in that they are located in the database, but they are not the same as data. And because they are separated, you can have the same system being used by multiple instances of your world. For example, the same system can be used by multiple games being played in supposedly completely different worlds that don't need to communicate. The default access control is that reads are always allowed. Why? Because we're on the blockchain. There are no secrets on the blockchain. Everything that you put on the blockchain is universally known. So letting people prevent reads when there's an easy way around it is probably not a good idea. Writes, on the other hand, have to come from a system in that namespace, and because we can have multiple namespaces and each one can have multiple systems, and those systems help control the data in that namespace. And you can modify, and this is just the default access control. You can modify it as needed. The reason for this is to allow for permissionless extensibility. I would love to talk about it, but it's too early. That part is still work in progress. I hope to be able to talk to you about it in the future. In that case, why would you use MAD, especially now? Well, it helps when you want to make something complicated, like a large on-chain game. And here are a couple of examples. OPCraft was Minecraft on top of an OP stack chain that didn't have transaction costs. And in just 10 days of running, it did 3.5 million transactions. It allowed people to walk around the 3D world, and it worked fine. Another example, more recent, is Words 3. That's an on-chain Scrabble. The layers are priced based on the recent demand with variable rate gradual Dutch auction, and players are rewarded for words. If you make a word, you get some money, and to use letters, you have to pay money. Okay, how does this work? First, you have the blockchain. Within the blockchain, you have the world, which is essentially a group of contracts, which includes the database, and it includes the systems that can be used to change the data on the database. The systems are actually separate contracts, but you don't normally need to worry about that. So you have your database. Whenever anything changes, the database emits events, and you can have an optional indexer. You will see why you might want that in a moment, that includes a replica of that database. The user starts the application, a player starts playing the game. Yay! One of the first things the application does is it builds its own database replica. And it could do it by going back to when the world was first deployed and looking at all the events. That could be slow. It depends on how recent the world is, but if it's a game world that has been running a long time, it's going to be a problem. So what's the solution? It can talk to the indexer and get the initial state from the indexer. And then as the world is ongoing, the database keeps changing. The events are the database replica in the indexer listens to the events, and the database replica in the application also listens to the same events, and it gets updated. That way, all of the information that the world has is also in your replicas. And okay, the player walks around, plays with various things. Eventually, the player will want to do something that changes the world state, right? They do it using a function call that goes to the world, and from the world, the system. The system then updates the database, and of course, this update causes an event that the database replicas can use to update their information. Now, you're saying to me, Ori, that's nice, but this is advertised as autonomous worlds and zero knowledge. How does this interact with zero knowledge? I'm glad you asked. In zero knowledge, there is always private state and public state. The private state is known to a single client. For example, the movements that the player is planning in the future, or random values that only one client should know, and facts that can be communicated to the public as needed. The zero knowledge proofs are used to communicate state so that you can make it public in a trustworthy way. And the zero knowledge proofs ensures honesty. It ensures that if a player tells you, well, 10 minutes ago I did this, it's something that the player really decided 10 minutes ago, and not something that they decided 5 minutes ago after they saw what was happening and made the decision based on that. The public state, that needs an authoritative source, which typically lives on chain, and it is replicated in the clients. This is where MAD can help you. We can hold the public state. We can make it easier than using Solidity storage. Here's an example. A random number, and you need to reveal some bits. There are two numbers. There's rpriv, which only one player knows, and then there's rpub, which is somehow derived on chain. Everybody knows rpub. The player then calculates the hash of rpriv and sends that to the public state so that everybody else also knows about it. Now let's say that the game is where you need to reveal bits 0 to 10 of the random number. If a zero knowledge function typically has two types of inputs. public inputs and private inputs. In our case, the public inputs are our pub, H, which is supposed to be equal to the hash of our priv, and which bits to reveal. And the private input is, of course, our priv. And this function is supposed to make this calculation. If our H is equal to the hash of our priv, which remember our function knows our priv, then it gives us the XOR of our pub and our priv, so that it calculates the XOR of our pub and our priv, so that neither side will be able to bias the result to be 0 or to be 1, and it gives us, of course, only the bits that we want. If H is not equal to the hash of our priv, then it returns 0, because, come on, the user is doing something wrong. Now, when we communicate this to the public state, we give our pub, which the public state already knows, so that if we put something incorrect there, they'll catch us. We have H, which is supposed to be hash of our priv, which again the public knows. And because the public knows it, they also know that we used the correct our priv, and of course which bits we're revealing. Okay, conclusion. Blockchain development is not trivial. Why? For one thing, state changes always have a cost. A state change is something that has to be processed by a whole bunch, by all the nodes in the system. That's going to cost something. Otherwise, we are way too open to denial of service. And we have to assume a hostile environment. If everybody were trustworthy, we wouldn't really need a blockchain. We use a blockchain because we assume that some entities, some users are going to try to cheat. And that's why we can't afford to have a centralized location that is the source of trust. We have to be distributed. To get those things, it is important to do data storage correctly. First, assume that everything is readable. Remember, there are no secrets on the blockchain. So assume everything is readable, because it is. People who run a node can know the value of any storage cell anywhere. Writes, on the other hand, need to be authorized, they need to be non-reentrants, etc. And for autonomous worlds, we need to have a local copy so that we can be responsive, so that when a user goes to a new area, say, they don't have to sit there twiddling their thumbs and waiting and getting impatient and thinking maybe they should do something else while we're loading state from the blockchain. You don't need to use MUD to get all of those things, but MUD does make it easier, and that lets you focus not on building infrastructure that we in Lattice have already built for you, but on building whatever it is you actually want to build. Thank you very much. And this is a recording, so I can't ask you for questions. But if you have any questions, you can always email me, ori@lattice.xyz.